This is where we are, right? What was I saying? I needed to sketch the face portrait, okay? So this is where we are. So my solution turned out to be C1 e to the negative 2t, help me out with this, 2, 3 plus C2 e to the negative t in 1, 1, right? So this is what is my solution, correct? So now the question is, what happens as t goes to infinity and as t goes to negative infinity? Now, as t goes to infinity, you can see that my first term goes to 0, my second term goes to 0, so my solution also goes to 0. Do you see that? Yes? As t goes to infinity, you can see that my solution x of t goes to 0. But you can see that e to the negative 2t to 3 is a smaller term. But e to the negative t in 1, 1 is the larger term. Okay? Larger term. And this corresponds to the eigenvalue negative 1. So my solution is x of t will behave or greatly influenced or behaves like or dominated by e to the negative t times 1 and 1. Does that make sense? Now as t goes to negative infinity, you can see that my solution x of t becomes infinite or unbounded. Why? Because when t is negative infinity, both the exponential terms goes to infinity, so my solution becomes unbounded. Do you agree with me on that? And when the solution becomes unbounded, you can see that e to the 2t 3 is the larger term or the dominating term, whichever way you want to look at it, is the larger term or the dominating term. So my solution is greatly influenced or dominated by or my solution is greatly contributed by this term e to the negative 2t to 3 here. Do you agree with me on that? Yes? So this corresponds to the eigenvalue negative 2. So that means, what does that tell you? That tells you that when the solution is near 0, it is near the eigenvalue lambda, it is influenced by the eigenvalue lambda equals negative 1. And when the solution is becoming unbounded or larger or for greater values of for t going to negative infinity, my solution is near lambda equals negative 2 or parallel to negative lambda equals negative 2 or influenced by the eigenvalue lambda equals negative 2. Does that make sense? Is that clear? So now what I said was at that time was, so when the solution is near 0, it is influenced by the eigenvalue lambda equals negative 2. So that means it is really starting out So when it is going to 0, it is influenced by lambda equals negative 2 here, and as the solution becomes unbounded, it is influenced by the negative 1 eigenvalue. So this tells you that it is going in this direction. Is that clear? So near the origin, it is following the blue line, and near the as the solution moves away from the origin, it is either parallel to the eigenvalue negative 1 or closer to the eigenvalue negative 1, like that. So this is how your solution curves would look like. Does it make sense? Now this side, it is going to be either this way. So that's how you're going to draw your face portrait. Make sense? So from here, I showed you yesterday that such a critical point is a sink, is asymptotically stable, and you complete the face portrait like that. Clear? You all good? So, any questions on that? No. Okay, let's move on to this is a simulation of the same thing. Now let's move on to the other one I want to tell you is this. my solution x of t is going to be c1 e to the negative 2t 2 3 plus c2 e to the negative t in 1 1. So in the previous lecture I demonstrated let's say x1 is e to the negative 2t in 2 3. So I want to tell you that x1 is the solution of the system of first order differential equation x prime equals ax. Do you agree? I demonstrated it in the previous problem. Are you comfortable with that, or do you want me to show it one more time?
Can you show one more time?
One more time. Okay, so this one x1 is going to be 2 times e to the negative 2t and 3 times e to the negative 2t. So I get x1 prime is going to be, when I differentiate it, negative 4 e to the negative 2t and negative 6 e to the negative 2t. Okay. Then now is it the solution of x prime equals ax? So I'm going to multiply with ax 1 here. So the matrix A is given to me by 1 negative 2 3 negative 4. So I'm going to write this as 1 negative 2 3 negative 4 times my x1, which is going to be 2 e to the negative 2t 3 e to the negative 2t. In my vector A, my matrix A is 2 by 2. My x1 is 2 by 1 vector, so matrix multiplication is well defined and you're pretty comfortable with that. So that gives me 2 e to the negative 2t minus 6 e to the negative 2t, and this is going to be 6 e to the negative 2t minus 12 e to the negative 2t. So this will lead me to negative 4 e to the negative 2t and negative 6 e to the negative 2t. So from here you can see that x1 prime is going to be ax1. So x1 is the solution of the system x prime equals ax. Is that clear? Are we good? Everyone okay with that? Yes.
Why do you go through the a times x1 if you can just take the derivative?
Can you repeat it a little loudly, please?
Why do you do the a times x1 if you can just do x1 prime?
Oh, okay, when is x1 a solution of this? Means when I substitute it, I should get x1 prime equals ax1. See, when something is a solution, I need to plug it into the equation and check both sides are equal, right? It's an identity. Do you see that? Is something a solution to an equation? Means what do? You substitute it into the equation and make sure that you get an identity on both sides. You get an identity. That means both sides are equal. Do you agree with me on that? So when I substitute x1, when I evaluate x1 prime, I'm getting this. When I multiply ax1, I'm getting that. So both sides are equal. So I'm getting an identity. Hence x1 is a solution. Is that clear? I can't see you, so you should.
Yeah.
Yes. Convinced? Okay. Are you all good? So this tells you that x1 is a solution. So is it okay if I say similarly x2 equals the other one e to the negative t times 1 1 is the solution of the system x prime equals ax. Is that okay with you? Do you agree with me on that?
It's the same method, right?
Say that again.
If you want to prove that it's the same method.
It's the same thing. You are going to say x2 prime equals ax2. So you're going to find out what is x2 prime and you're going to find out what is ax2 and say both sides are equal. Yes. Are you okay with that? Can I just skip that? Say yes, nod your head, smile, thumbs up, something. Okay. Then the next thing I want to tell you is that these two vectors are linearly independent, and we discussed in the last class you can establish linear independence if the determinant is non-zero or if the Wronskian is non-zero. So in this case you get e to the negative t, e to the negative t, and 2e to the negative 2t and 3e to the negative 2t. When you find the determinant, what you get is 3e to the negative 3t minus 2e to the negative 3t, and you will see that's not equal to 0. So Wronskian is not 0. So x1 and x2 are linearly independent. Clear?
Can you just remind me what the Wronskian is?
Wronskian is nothing but, bless you, is the determinant of x1 and x2. That's it. You see x1 is e to the negative t and e to the negative t, and x2 is going to be 2e to the negative 2t and 3e to the negative 2t. So that means you're taking the determinant of both the vectors. That tells you if the determinant of the vectors is non-zero, hence the vectors are linearly independent. Is that clear? So now, because these vectors are linearly independent, and so here x1 and x2 are the solutions of the system x prime equals ax, and the next one is x1 and x2 are linearly independent, and they are linearly independent because the Wronskian is not equal to 0. So you can conclude by saying x1 and x2 form the fundamental set of solutions, solutions for the system x prime equals ax. Clear? Are you all good? Clear? Okay, so that finishes out this problem. So let's begin with this problem here.
Wait, can you go back for just a second? Yeah, what's FS?
Is a fundamental set.
Oh,
Okay, let me write this. Okay? All good? Okay, let's look at a different problem. Negative 2, 1, 5, negative 4, right? So x prime is negative 2, 1, 5, negative 4 times x, right? Now, the step 0 is to find the critical point. I mean, or the first thing is you want to find critical point. So to find the critical point, what do? You set x prime equals 0. So when you set x prime equals 0, you get, ax equals 0, where your a is negative 2, 1, 5, and negative 4, right? So you can see that the determinant of a is equal to 8 minus 5, so that equals 3, and not equal to 0. So a is a non-singular matrix, right? You know that. Not a really a surprise. So a inverse exists. So if a inverse exists, you can multiply both sides by a inverse. Then what you get is going to be x equals 0 is the critical point. Do you agree with me on that? So first thing is you're making sure that for this problem, for this system, 0, 0 or origin is the critical point. Remember, when I write 0, this is not a number, this is a vector, this is a point. Because this is a system, this is not a how do I say? This is not a scalar, it's 0, 0, it's an origin. Okay, remember that. Keep this in mind. Okay? Clear? Are you all good? Okay? Then the next step is to find the eigenvalues. So are you comfortable with saying 3, negative 1 would be my eigenvalue? Or do you want me to show that? You must have seen that lambda squared minus lambda times trace plus determinant is equal to 0 because it's a 2 by 2 matrix. So you get lambda squared minus 2 lambda and the determinant turned out to be plus 3 equals 0. So you can write this as lambda minus 3 times lambda plus 1 equals 0. I hope I'm right on this. Am I right? I'm wrong. 4 times negative 2. I don't know why I did this. Negative 2, 1, negative 5, and positive 4. Nobody told me that. Okay, so negative 2, 1, that. So this is negative 8, positive 5. So this is negative 3. But nothing really changes after that, but still. Okay. So in this case, I got negative 3. So this gives me lambda minus 3 times lambda plus 1 equals 0. So this tells me that my eigenvalues are 3 and negative 1. So this is what I have. Is that good? Are we good? So can I now step 2 is to find the eigenvectors. So I want to say when lambda 1 is 3, the eigenvector is 1, 5. Are you comfortable with that? Can I just skip the work?
Can you just, could you state it?
Say that again.
Can we just get some time to write this down a little bit? Or could you explain that?
You want me to explain how the eigenvector is 1, 5? Okay. So the way I'm going to do is when lambda 1 equals 3, I'm going to go a minus 3I times v equals 0, right? So that means I'm going to subtract 3 from the main diagonal. So I'm going to get, I hope I get everything right. So negative 5, 1, negative 5, and the other one is 4 minus 3 is 1 times v1, v2 is 0, 0. So by performing the row operations and reducing it in row echelon form, you pretty much get negative 5 v1 plus v2 equals 0. This is a homogeneous system of equations, so you will have either trivial solution or non-trivial solution, but you will end up getting a free variable, so you will have a non-trivial solution. So you get v2 is going to be 5v1, so your v is going to be really v1 in 5v1, and your when v1 is 1, your v is going to be 1 in 5. So that's how I'm going to get that. Is that clear? Okay. Are we together? Okay, so the next thing is when my eigenvalue is negative 1, my claim is my eigenvector will be 1, 1. Are you on board with that? Running through the same process. Okay? So from here, I would get my general solution. X of t would be c1 e to the lambda 1 t times v plus c2 e to the lambda 2 t times w. So here, lambda 1 is 3, lambda 2 is negative 1, v is 1, 5, w is 1, 1. So I write my general solution like that. So step 0 is to find the critical point, step 1 is to find the eigenvalue, step 2 is to find the eigenvector, step 3 is to write the general solution. So I did that. So this is my general solution. Now we're going to spend some time on understanding the general solution. Is that clear? Everyone okay? Okay, so let's move forward with this one. So I have this. So what happens as t goes to infinity? As t goes to infinity, you can see that as t goes to infinity, you can see that e to the negative t times 1, 1 goes to 0. Do you agree with me on that? 0, 0. Okay, not 0. It goes to 0, 0. You agree with me on that? Whereas e to the 3t times the 1, 5 becomes infinite. I mean, because t is going to infinity, so the first term is going to is becoming unbounded, becoming large, so it's becoming infinite. Do you agree with me on that? So your solution really, x of t is also becoming infinite, and your x of t is really almost behaving is greatly influenced by e to the 3t15 because that is the larger term. I mean, this is the larger slash the dominating term. And this corresponds to the eigenvalue lambda equals 3. Agreed? Yes or no? So now as t goes to negative infinity, what happens? I mean, you can see that e to the 3t times 1, 5 goes to 0, 0 now. Right? The first term goes to 0, but the second term e to the negative t 1, 1 is growing, becoming infinite. So e to the negative t 1, 1 is the larger term or the dominating term.
Wait, how do you determine which term is dominating?
Whatever is not going to 0 is the dominating term, or whatever is the larger term, that is the dominating term, right?
So if there was one negative and one positive, like even if it was negative 5, 5 and the positive one was 1, 1, the 1, 1 would be dominating?
The dominating term is decided by what? Is decided by this, because the other one is just a scalar, right? So as t goes to negative infinity, this exponential term is becoming positive. That is what is growing, and that is what is the larger term. Whereas e to the 3t will become e to the negative term, and e to the negative is always less than 0, is less than 1. So that's a smaller term, right? Okay. Are we all together? Okay. Then your solution is greatly influenced by e to the negative t in 1 and 1. So what does this tell you? This tells you that when your solution is infinite or unbounded, I mean as t goes to infinity, the behavior is this way. When your solution is infinite and unbounded, but as t goes to negative infinity, it's influenced by e to the negative t or corresponding eigenvalue lambda equals negative 1. Do you agree with me on that? Okay? Yes or no? Keep this in mind. We'll come back and tie it up in a few minutes in the phase portrait. So the next thing I want to tell you is, okay, my matrix is negative 2 x prime equals negative 2, 1, negative 5 and a 4. So my A is going to be negative 2, 1, negative 5 and a 4. Do you agree with me on that? So the next one is, let's say if my if I'm really standing at, like now I'm really speaking in a goofy way, humor me for a few minutes. So that means 3, 0. That means 3, 0 means what? It is like I'm really standing here. Okay? Are you with me on that? Let's say my position vector is 3, 0. What is happening to me? Where am I traveling? That's the next question. If I'm standing at this means, you know, I'm really evaluating AX. So this is going to be negative 6 in negative 15. Do you agree with me on that? So this is AX is X prime. So that means if I'm really standing at 3, 0, my I'm being pushed in the direction of negative 6 and negative 15. So I'm pushed to the left into the bottom. So that means I'm pushed in that direction. Do you agree with me on that? Yes?
Is the arrow based on the slope or is it just like the general direction?
It's the direction. The slope will be, what will be the slope? I'll get it back to that in a moment, but I'm just pushed in that direction. That's all. That's all the claim that I'm making right now. Okay, so then if I'm standing at negative 2, 1, negative 5, 4, a point on the y-axis, 0, 3, then what am I experiencing? I'm experiencing 3 and 12. So that means if I'm standing at this, 3 units to my right and 2 units above, so I'm experiencing force in the direction. Or x prime is that, so that means velocity is that, so I'm being pushed in that direction. Do you agree? So now if I pick a point negative 2, I mean there is nothing sacred about 0, 3. You can pick 0, 1, 0, 2, anything, but I just picked 0, 3 to be a little away from the horizon. Negative 2, 1, negative 5, 4, and I'm picking a point on the negative x-axis, negative 3, 0. So that gives me 6 and 15. So if I'm really standing here, then I'm experiencing the force in that direction. Do you agree with me on that? 6 and 15 means 6 units to my right, 15 units to the top. So I'm experiencing the force in the top right direction. Okay? Yes? You're not convinced. You're just shaking your head. But I'll give you a few minutes. See if you still have questions, let me know. Okay? I see the sad thing is I don't know your names. I cannot ask you by name, but if you don't ask me questions, what is the point in my standing and teaching, right? 0, negative 3. Don't go to the YouTube. I swear by God. Yes. Can I complete this or do you have a question?
Yeah.
Yes, what is it?
It basically, so basically, I was a bit confused.
Say that again.
I was a bit confused by the face portrait at first, but basically it seems like the face portraits are kind of like, there's still like the same differential fields that we're used to, but like instead of starting out with a number, we basically just start out with like a point.
I'll explain that in a moment. Okay? Let me first sketch the face portrait and then I will compare and contrast with direction fields and stuff like that. Okay? Okay, so if I'm doing it 0, negative 3, what do I get? I get negative 3 and negative 12. So that means if I'm here, I'm experiencing 3 units to my left and 12 units down, so I'm going in that direction. Right? Do you agree with me on that? Now, I want to draw, 1, 5. So, 1 and 5, 2 and 10. So, allow me 1 and negative 5, 2 and negative 10. So, if I'm draw, this one would be my eigenspace for lambda 1 equals 3. Right? Yes or no? And this one is 1, 1. So let me choose a different color. So 1, 1 means, this is 5, 5. That is 10, 10. So I can draw that and I get one that. So I get that. This is corresponding to lambda 2 equals negative 1. Do you agree with me on that? Yes? Yes or no? And now, because the eigenvalue is 3, that means as the t goes to infinity, you are going away from the origin. That's why the arrows are indicated outbound. Okay, that's why I'm drawing an outbound arrow. And here the eigenvalues are negative. You see in the previous one I made as t goes to infinity, e to the negative t goes to 0, 0. And that's why they are inbound. I'm drawing an inbound arrow here, right? So I'm drawing an inbound arrow. Is that clear? Are you all good with that? Yes or no?
Yes.
Okay, now the next thing is I want to draw the face portrait. Now, face portrait would be there. It is, now you go back to your behavior. Now, as t goes to infinity, your behavior of the solution is like this, and it is dominated by the eigenvalue lambda equals 3. So it is dominated by lambda equals 3. So that means you are at lambda equals 3 is somewhere here is my lambda equals 3. And the next one is as t goes to negative infinity, your behavior is dominated by lambda equals negative 1. So that means you're really traveling from lambda equals negative 1 and going like that. Is that clear? In here, you're traveling from that and you're traveling this way. Okay, is that clear? So if you're, now the values of C1 and C2 are arbitrary. Now, as you keep varying the values of C1 and C2, you're going to get a different solution curves like that. Okay, and the same thing here as well. So, the bending, the amount of the curvature or the amount of bending of my solution curve may not be exact, or the place of bending may not be exact, but I'm just generally giving you a behavior as to how my solution curves will travel in a 2D plane. Are you with me on that? Now what happens in the middle? Here you see the solution curves travel like this, and then they turn around and follow lambda 1 equals -3. Here the solution curves will travel like this and travel around and go to follow lambda 1 equals +3. But the solution curves will never go to 0 is given by the fact that, I mean, as t goes to infinity, my solution becomes infinite. As t goes to -infinity, my solution becomes infinite. My solution becomes infinite here as well. So it will never go to 0. So my solution is never going to 0. Instead, it is going this way. Is this clear? Now, just to, I mean, so what can I conclude? I can conclude by saying that, my solutions are going away from the origin. So I can say 0, 0 is an unstable critical point. Unstable critical point, and 0, 0 is in fact a saddle point. Okay, is a saddle point. It is not asymptotically stable. It is not stable. It is unstable because the solution curves are going away from the origin. They are never able to converge to origin, so that's why it is unstable. Okay. I'm going to talk a little bit more. So hold your questions for a few minutes, and I'll speak to you in a moment from now. Are we together so far? So what did I do? I did the first step is to find the critical point. The second step is to find eigenvalues, then eigenvectors, write the general solution, and then find out what is my dominating term, and then draw my arrows in which direction are my curves moving, and then I drew my solution curves. Is that clear? Yes? Now, if you look at my solution here, let's say my t equals 0, for example. Then my solution x is going to be C1, 1, 5 plus C2, 1, 1. And now let's say my C1 is 1 and C2 is 1. Then this gives me 2 and 6. So it is like saying, okay, when my x value is 2, my y value is 6. I mean, my sketch is so bad, but somewhere there. Are you with me on that? Then if you say, okay, if my instead if I say C1 is -1 and C2 is -1, then it will be -2 and -6. So that means it is -2 and -6 somewhere at the bottom here. Are you with me on that? So -2 and -6 means somewhere here, and +2 and +6 means somewhere here. So that's what is the solution. That's what is my position when at t equals 0 and when C1 is 1 and C2 is 1, or C1 is -1 and C2 is -1. So the solution curve is telling me where exactly I am in the time at the particular time. Does that make sense? Yes or no?
What are the 2 points on the graph?
Which points on the graph? This point?
I don't know what you're doing, but like
This one. I'm writing it for you. Oh. Are you talking about this one?
Right by the red line. By the lambda equals -1. There are 2 points.
This one? This one?
Yeah.
Okay, that one is for a different C value. If I pick some C1 to be very small and C2 to be very small, my solution may be lying right there. That's what I'm saying.
It can be closer or farther.
So it depends on where my C1 and what my C1 and C2 values are. So I get different points. That's all I'm trying to say.
Okay.
Make sense? Clear? Are you all okay with that? Now solution curves. These are the solution curves. The solution curves are pretty much the plots of the solution here. And if you want the direction field or vector field, you just you just go based off on the matrix here. That will be the difference. The vector field will be describing the differential equation, where the solution curves will be describing the solution. Okay. Now, if you go back, broadly speaking, I showed you 4 different pictures. I don't know where it is now. Here, you see when the eigenvalues are of opposite signs, it is a saddle point, and it basically looks like that, the rough sketch of it. I mean, this is a typical scenario, and that is exactly what we got in this problem as well, okay? That is what we got in this problem as well. And using the computer, that's how the simulation would look like. Clear? Any questions? Is this clear? So you will see a problem like this on the quiz and on the midterm and on the final exam. There are no two ways about it. Since from the time human beings learned about the face portraits, they have been drawing it this way by hand, but really nobody does it now this way because the computers are there, they'll simulate it and all that. But this is an important problem that will, from the test perspective as well, you will find eigenvalues, eigenvectors, write the general solution, sketch the face portrait, and then classify the critical point. So 5 questions rolled into one, approximately 20 points. So clear? All good? Any questions? Now you have seen 2 problems, so pretty much from now on is going to be you are going to work out several different ways and go about it. So this problem is the next problem is x prime equals 5 negative 1 3 1 times x. So your matrix A is going to be 5 negative 1 3 1. So you want to find step 0 is to find critical point. To find a critical point, you're going to set x prime equals 0. So this means ax equals 0. So you can see that the determinant of a here is going to be 5 minus 3, which is going to be 8. So that's not equal to 0. So a is non-singular. Okay, a is non-singular. So a inverse exists. Okay. So you can write this as A inverse AX. You don't need to write it every single time, but I'm just writing it so that you are aware that this is how we are finding it. A inverse times 0. So this gives you x equals 0 is the critical point. Remember, when I want to draw your attention, this is not a number, it is origin that we are referring to. Okay, 0 is the critical point. Make sense? All good? Yes, Alfie.
What is A inverse times A, like A inverse? I'm just doing the identity.
A inverse times A is I.
Yeah.
You're multiplying both sides by A inverse. So A inverse times A is I times x is 0. So I times x is the vector x. So that's going to be 0 again. Right? Say that again.
I was just confused how you set it equal to A inverse times 0.
I'm multiplying both sides, but see, x prime equals 0. Okay, so x prime equals 0. Because x prime is 0, ax equals 0, right? Because A inverse exists, I'm multiplying both sides by A inverse.
Oh,
It's like multiplying both sides by A inverse. That's what I'm doing. And that leads me to this. Okay? Okay?
What would, just a question, what would happen if the determinant was 0?
Fantastic question. That will be the next problem. Like if you give me 10 minutes, I'm getting there. Very good. You just preempted. You're not playing the problem, you're playing me now. Okay? So very good question. That's the next problem. Okay? Just 15 more minutes hopefully and we are there. So this is a problem. That's really nice, right? Somebody is like, no? There might be other people who already think about it, but you're not saying it. Yeah, So the step 1 is to find the eigenvalues. So the eigenvalues are those two. Okay, do you agree with me on that? I mean, can we just safely assume that? Oh, he just left. He asked me to compute the eigenvector and then he left. That's fine. Next time I'm going to know his name. Okay? You leave my class, I find your name. How about that? No, I'm just kidding. I will not. Let's go back. Sorry. So we want to find the eigenvectors, and let's say for the eigenvalue 4, the eigenvector is 1, 1. For the eigenvalue 2, the eigenvector is 1, 3. Are you on board with that? I mean, I'm skipping computations. I'm gonna request you all to trust me on that. Okay? Clear? So now, so here you see this x1 is going to be e to the lambda t times v, lambda 1 t times v. So that's going to be, for me, it is going to be e to the 4 t times 1, 1. X2 is going to be e to the lambda 2 t times w. So that's going to be e to the 2 t times 1, 3. So my general solution x is going to be C1 e to the 4t times 1, 1 plus C2 e to the 2t times 1, 3. Right? Do you agree with me on that? And that's my step 3 is to find the general solution. And my general solution is here. Correct? Clear? So let me ask you this question, which I'm sure you will know this. So when my eigenvalues are negative, my critical point is 0, 0. So all my solution curves are going to 0. Do you agree with me on that? And the arrows were inbound on the eigenspaces. Do you agree with me on that? And when one of them is positive, one of them is negative. So for the positive eigenvalues, the arrows are outbound. For negative eigenvalues, the arrows are inbound. And my solution was never going to 0. Do you agree with me on that? So if my eigenvalues are both positive, what would you expect? Are the arrows on the eigenspaces outbound or inbound? Outbound. Does the solution go to 0 or become infinite? Infinite, right? As t goes to infinity, it becomes infinite. So this case will be really opposite of the case when eigenvalues are real and different and negative. Do you see that? Yes or no? So let's see that a little bit in detail. So now as t goes to infinity, what happens? E to the 4t times 1, 1 becomes infinite. And e to the 2t times 1, 3 also becomes infinite. So your x of t, the solution also grows to becomes unbounded. So the solution also becomes infinite. Do you agree with me on that? But between these two, which one is the larger term? E to the 4t is the larger term. So this is the larger term or the dominating term, right? So this corresponds to the eigenvalue lambda 1 equals 4. So this means as t goes to infinity, your solution will be pretty much dictated by this term. Do you agree with me? Yes or no? So when the solution is becoming infinity, or when the solution is becoming infinitely large, it is really dictated or influenced by the eigenspace where the eigenvalue is 4. So that means it will be on that line or parallel to that line. Do you follow me on that? Okay. So that takes one part away. Then as t goes to negative infinity, what do you think will happen to the e to the 4t 1, 1? It goes to origin, right? Correct. Then what happens to e to the 2t 1, 3? Origin, right? It goes to origin again, right? Do you agree with me on that? But what is the dominating term here? This is the dominating term or the larger term. Do you agree with me on that? Okay. Then what happens, because both the terms are going to 0, my solution is also going to the origin, but my solution is really dictated by e to the 2t 1, 3. Do you agree with me on that? So near the origin, I'm near the eigenspace corresponding to the eigenvalue 2, and away from the origin, I'm near or parallel to the eigenspace with the eigenvalue 4. Do you agree with me on that? Yes? Keep that thought in mind. I'm not writing it. That's a very important thought. So let's sketch the phase portrait now. So 1 1 would be, that is 1 1. So that's 1 1. So eigenvalues are positive, so the arrows are outbound. So lambda 1 equals 4. The other one is 1 and 3, 2 and 6. Okay, 1 and 3, 2 and 6. Change the color, sketch the line. Right? So that's lambda 2 equals 2, right? Do you agree? Yes, I think I got it pretty much, right? But now, how can, oh, no, I need to draw the outbound arrows here as well. Okay? Yes? Now, I want to get that, remember that direction, like how much force I'm experiencing. I want to do that. So, I'm going to do it like, okay, 5, negative 1, 3, 1 times 3, 0 for a point on x-axis. This is going to be 15 and a 9. So, that means 15 units to the right, 9 units to the top. So, I'm going in that direction. Agreed? Then I'm gonna do the same thing for a point on the y-axis. I'm picking a representation of that 0, 3. So that's gonna be negative 3, positive 3. Hopefully my multiplication is right. If I'm wrong, correct me. Negative 3 is 3 units to the left and 3 units is to the right. So to the top. So that's where I'm going. And now I'm going to pick a point 5, negative 1, 3, 1, and a point on negative x-axis. So that's going to be negative 3 and a 0. So that's going to be what? Negative 15 and negative 9. So that means negative 15 is 15 units to the left, negative 9 is 9 units to the bottom. So I'm going that way, right? It's obvious, right, for you? Now, so this will be 5, negative 1, 3, 1. Then 0, negative 3 is, if you do that, you get 3 and negative 3. So that's 3 is that in negative 3, positive 3 is 3 units to the right. And negative 3 is down. So I'm going that way, right? Hopefully my computations are right. If I'm wrong, please correct me and let me know. Right? Yes.
Since it's going from 0, negative 3 to 3, negative 3, could you just go straight to the right? Because it's that still a while.
0, 3 to negative 3 to 3. Is this the one you're talking about?
So you start at 0, negative 3.
Or this is the one you're talking about?
You started at 0, negative 3, and then went to 3, negative 3. So,
No. Oh, I see. Answer is yes. But what I'm not getting to the scale. I'm just saying, okay, 0, 3. Negative 3 means I'm moving 3 units to the left and 3 units to the top. So I'm going in that direction. That's all I'm trying to say. I'm not indicating exactly, like that.
it's why it's here, that's it from that.
Right. I'm just indicating the direction. Is that okay?
Yeah.
Okay. So now let's go back to this. So in here, I said my solution is becoming infinite. As t goes to infinity, my solution is becoming infinite and dominating term is corresponding to lambda 1 equals 4. And as t goes to infinity, my solution goes to origin, but the dominating term is lambda equals 2. So when I'm near the origin, my solution curves are near the eigenvalue 2. Do you agree with me on that? So that means I'm starting out here. And then as the arrow indicates, I'm bending and I'm moving to the top and going parallel to that. So I'm moving away from the origin, so I'm going to draw my curves like that. I mean the rough sketch, so don't really read anything much into it. So that's how I'm going. You with me on that? So now what is happening here? If you see the other side of it, I'm going close to the red line and then moving and then going parallel to the blue line or the eigenvalue lambda equals 4. So my solution curves are really going that way. Okay? So what's happening in the middle? I mean, near the origin, I'm very close to this and then I'm going parallel to the blue line. So that means I'm here, and here I'm going parallel to that and going that way. So that's how I'm getting it. Is that clear? Yes.
So can you look at any of the stability of the eigenvalues?
I will.
Okay.
The stability of the critical point based on the magnitude of, based on the sign of the eigenvalue. Okay. I did not answer that for this one at all so far. I wanted to get the, because remember, critical point, eigenvalues, eigenvectors, general solutions, phase portrait, and then stability. I'm going in that order. But you could, the moment you get eigenvalues, you know the stability pretty much. So you didn't have to wait this long. But yes, I'm going to say that in a moment from now. Is this clear? And the simulation version would be that. Now the stability would be step 5. I mean, sketching the phase portrait is step 4. Step 5 is a stability. So the critical point is unstable. Why? Because they're going away from the origin. Do you see that? It starts from the origin and goes away from the origin. So critical point is unstable. And the critical point is, because everything is going out of the origin, critical point is a source or the repeller. When it is negative, it is a sink or the attractor. I studied in the context of the bar magnet, like, you know, everything magnetic field goes into something. It's called a sink. The other one, it goes out of it. I forgot. Gets out of the North Pole and converges to the South Pole or something like that. Magnetic, non-magnetic pole. Anyway, I could be wrong. I studied several years ago. So sink and source is basically in that terminology. So critical point is source and repeller. Is that clear? Are you all good with this? Yeah.
How do you know that the eigenvalues are like outbound, like errors?
How many of you had that question and did not ask me that? You shouldn't. Okay, no problem. Now thank you for asking that question. Okay, e to the 4t, and the next one is what? Plus. Okay, now C1 and C2 are arbitrary constants, right? Let's just say hypothetical case C1 is 1 and C2 is 0. It should satisfy for all values of C1 and C2, so I'm picking 1. So my solution is really 1, 1 e to the 4t. Do you agree with me on that? So as t goes to infinity, you see my solution is going to, my solution is growing and it is becoming infinite. So it is going away from, in other words, no, let me not do that. This doesn't give you the contrast. So x of 0 is 1, 1. Do you agree with me on that? So, but x of 10 would be what? 1, 1 times e to the 40. So that has grown, right? So that means it has traveled further away from the origin. So that means that tells you that, okay, if I'm here, 1, 1 would have been somewhere here, but when t is 10, 1, 1 e to the 40 would have been somewhere there, right? I mean, you know, on a rough scale, okay? So that means it has traveled away from the, as time progresses, you're going away from the origin, and that's why it's outbound. Make sense? Now, let me also add one more thing. Let's say if my C1 is -1 and C2 is 0. So what is my solution? It is negative of 1, 1 e to the 4t. Do you agree with me on that? So if t is 0, then my x of 0, is -1, -1. But when t is 10, my x of 10 would be -1, -1 times e to the 40. So that means it would have been somewhere, -1, -1 is here, but at t equals 10, I would have gone in that direction, so further in that direction. So I'm again moving away from the origin, and that's why they are outbound. Make sense? Now you can repeat the same logic. Okay, put C1 is 0 and C2 is 1, and for the other eigenvalue. Clear? Clear? Yes? Lot of people said it, but somehow these two faces registered in my head. Are you both okay? Questions? You good? All good? So that finishes this problem out, okay? So, I mean, this is unstable and all that. Now let's go back to Romel's question. What happens when the determinant is 0? So we should pick up a problem that tells you that, right? So this is a problem, -1, 4. So you saw one problem. Where eigenvalues are real, indifferent, and positive. The other one is where the eigenvalues are real, indifferent, and negative. The eigenvalues are real and different and of opposite signs, right? You finished out 3 problems. Now, what happens when one of them is 0? Okay, what do you know about 0 eigenvalue? I mean, if one of the eigenvalues is 0, what can you say about the matrix? Yes?
It's not invertible.
Not invertible. Any other thing? Yes?
I guess it kind of
Say that again.
It only has like, mine only has like one solution.
Okay. So let's pick this problem. I have x prime equals -1, 4, 1/2 and -2 times x, right? So I want to find, step 0 is to find critical point. Do you agree with me? And when I want to find critical point, I want to set x prime equals 0. So which means I want to set ax equals 0, right? So I want to multiply both sides by a inverse, but I want to make sure that an inverse exists. So I want to find what is my determinant of a here, okay? Determinant of a is going to be what? 2 minus 2, which is going to be 0. So a is singular. So a inverse does not exist, right? So if a inverse does not exist, so how do I find my critical point? I'm going to say, okay, I'm going to write this as, ax equals 0 means -1, 4, 1/2 and -2 times, x1 and x2. Remember, x1 and x2 are components here, not really solutions. Equals 0, 0. So you're going to perform elementary row operations, obtain row echelon form, and that would give you, and there would be a free variable, and that would lead you to negative x1 plus 4 x2 is 0. So obviously x2 is going to be 1/4 of x1. So is that clear? So look at this previous problem. I mean, look at the beauty of the problem now. Because your A was non-singular, the origin was the critical point. Do you agree with me on that in the previous problem? Now, A is singular, so my critical point is not origin, but it's defined by this. What does that mean? I have a line of critical points. Fantastic. No bonus points, but fantastic answer. Okay? Because, this is in the form of y equals mx, so it's a line with a positive slope going from the bottom left to the top right with the slope 1/4. Every point on that line is a critical point. Do you see that? How many critical points do I have? Infinitely critical, many critical points. So this is a line of critical points. Or some textbooks refer to it as equilibrium line. So now, mentally thinking, so what happened when your eigenvalues are real, different, and negative? Everything went to the origin, right? When your eigenvalues are real, different, and positive, everything went away from the origin. Do you agree with me on that? So either they're going to the critical point or going away from the critical point. Now we don't have a point, we have a line. So everything should go to the line or go away from the line. Do you see that? Yes or no? Mentally speaking, that's what should happen. Yes? So let's experience that when we solve this problem. It's going to be really nice. Is it okay if I just say that, okay, when you find eigenvalues, the eigenvalues are 0, -3, and the eigenvectors are going to be those. Is that okay if I say that? If I just skip every computation and get there, are you comfortable with that?
Yes.
Okay, good. Thank you. So my system is x prime is gonna be whatever I have -1, 4, and 1/2 and -2. Watch my work. So my eigenvalues turned out to be lambda 1 equals 0 and lambda 2 equals -3. My corresponding eigenvectors turned out to be 4 and 1. And my corresponding eigenvector turned out to be -2 and 1. So my general solution turned out to be C1 4 1 plus C2 e to the -3t -2 and 1. Do you agree with me on that? Are you on board with that idea? Step 1 is to find eigenvalues. Okay, this is step 0 is to find critical points. So in this case, you got an equilibrium line or line of critical point. Step 1 is to find eigenvalues. Step 2 is to find eigenvectors. Step 3 is to find the general solution. You got that, right? Okay? So we're going to do the same analysis, right? As t goes to infinity, what happens? As t goes to -infinity, what happens? Just to, that because to know where our curves, solution curves are going and all that. So now, if you see this, as t goes to infinity, what happens? Can you tell me? Yes. Right. So you can see that e to the -3t very good, goes to 0, 0, right? So your solution really goes to C1 times 4, 1. Do you agree with me on that? So as t goes to -infinity, what happens? You can see that this is a larger term or the dominating term. Is going towards x of t is going towards that, not equals to what that. As t goes to -infinity, you can see that your solution x of t really goes to e to the -3t and -2, 1, and that becomes infinite and unbounded, right? So that is the larger term. Do you agree with me on that? Yes? So how would you graph it? 4, 1 means 1 and 4, 1 and 4, 2 and probably 8, so 1 and -4, 2 and -8, so it's probably that. Right? But because that is the equilibrium line of critical points, you're not really drawing any arrow on the critical point, line of critical points. Remember that. This is a line of critical points. Okay? Now when you see it here, as t goes to infinity, everything is going to the line of critical point. So you're pretty much saying that it's going to the critical point this way as t goes to infinity, or it is going to that way again. Clear? Yes.
Wouldn't the line basically be rotated a lot more towards 4, 1 instead of...
Did I? Yeah, you see, you're right. I got it wrong. Thank you for pointing it out. I apologize. I'm so sorry. 4 and 1, 8 and 2, right? So -4 and 1, -8 and... So my line of critical points is that. This is line of critical points. And as t goes to infinity, you see everything is going to the critical point, so you are graphing it like that. Okay? You with me in that? So now, the one thing is your textbook really doesn't talk about stability at this point. So you found eigenvalues, you found eigenvectors, you found the general solution, you sketch the phase portrait. The only thing is left is classification, but your textbook really doesn't. I have 1 more minute. Your textbook really doesn't say anything about stability. It doesn't say it is stable. It doesn't say it is asymptotically stable. It doesn't say it is unstable. It just remains silent. But the other one says this is there are several other textbooks that I know talks about it as equilibrium sink. That means the line is an equilibrium sink. Yes, you have a question?
Why do the lines approach, how do we know that the errors approach the line?
Because as t goes to infinity, I have C1, 4, 1. If C1 is positive, I'm approaching this way. If C1 is negative, I'm approaching downwards. Something like that. But for the different signs of C1, you will get different shapes. Okay? So that finishes this problem. And the simulation would look like this. If you have no questions, that is all I have for this class. We will continue from here in the next session.